there are some, like this one here. On the left side, you'll notice that we have two gallium atoms, two Ga atoms, and on the right side we only have one gallium atom. The same thing with the oxygens. We have three oxygens on the reactant side, but we only have two oxygens on the product side. So looking at this reaction, you might think that somehow a couple of atoms are destroyed. Well, we know in chemistry that that can't happen.
The law of conservation of mass says that atoms cannot be created or destroyed in a chemical reaction. So what we're going to do is take a little inventory here of the atoms that we have on both sides. And we have, there are two galliums and there are three oxygens on the left. And on the right, looks like we have one gallium and two oxygens on the right. And we're going to do something to this equation. It's called balancing it to make it obey the law of conservation of mass. Now, the first thing I notice is the oxygens are not balanced, so I'm going to somehow have to multiply these two numbers, the 3 and the 2, by something so that they'll equal the same value on both sides. Now, 3 and 2, if I multiply the left side by 2 and the right side by 3, well, I can have the same number of oxygens, 6, on both sides. So that's what I'm going to do. I'm going to multiply the right side by 3, putting a coefficient out in front. And so that multiplies whatever it's in front of by that coefficient. So 3 times 2 is 6 now. And I'm going to put a 2 over here in front of gallium oxide. And that multiplies the oxygen by 2, so we have 6. But notice that also multiplies the gallium by 2. So I don't have 2 anymore. I have 2 times 2, which is 4. So my oxygens are balanced, but my gallium atoms are not. So I have 4 on the left, 1 on the right. I'm going to multiply the product side by 4, and I can see that by doing that, I now have a balanced equation. I have the same number of gallium atoms on both sides, and I have the same number of oxygen atoms on both sides as well. So that's a balanced equation. It's obeying the law of conservation of mass. Now, some of you might find it helpful to make this little chart, this little inventory here to determine how many of each atom are on both sides. Some of you might not have to do that. Now let's say we have this reaction here. We have aluminum plus iron 2 sulfate yields iron and aluminum sulfate. Now the first thing I want you to notice is in this single replacement reaction, I'm going to actually treat the SO4 almost like it's its own element, because that makes things a little bit easier for us. For example, on the left, I have one aluminum, as you can see right here. I have one iron atom, and I have one SO4. Okay, that makes it a little easier. Now, you could say that there's one sulfur and 4 oxygens, but for me it's a little easier just to treat the SO4 like it's its own unit. And on the right, I have one iron, and looks like we have, actually let me change that to Al so we have everything on the right side here. Al, we have 2. Fe, there's 1. And the SO4, how many SO4s do we have? Well, there are actually 3, because that little coefficient right there tells us that we have 3 of them. So that's how we have that. Now, I want you to notice that our SO4s are not balanced. We have 1 on the left and 3 on the right. So I'm going to multiply this FeSO4 by 3. Okay, now the only way to balance an equation is by putting coefficients out in front. You can never change the subscripts or do anything like that. You can only put coefficients in front. So that's going to multiply the SO4 by 3. It's also going to multiply the iron by 3 as well. So we have that now. Now we have aluminum atoms. They're not balanced, so I'm going to balance those. We have 1 aluminum on the left,
This doesn't look very pretty, but we have 2 aluminums on the right. So I'm going to multiply this by 2, and my aluminum atoms are balanced now. All that's left is to balance my iron atoms. We have 3 on the left, 1 on the right. So I'm going to multiply the iron by 3, and now that one is balanced. Okay, so we've balanced a couple of equations. So that looks correct. So it's obeying the law of conservation of mass. Let's try another one here. We have 2. Let's take a look at the first one. On a combustion reaction like this, I strongly recommend that you balance the carbons first, the hydrogens second, and the oxygens last. All right. In fact, anytime you see an element, like over here on the right side that's split up, we have oxygens that are split up by a plus sign. I would recommend that you balance that element last, okay, because normally makes things easier for us. So when you see an element split up like oxygen is over here on the right side, balance that element last. Well, let's start with the carbons. This time I'm going to try balancing this without making a little inventory. Some of you might be able to do that. If you need to make a little chart, an inventory, go ahead and do that. But I'm going to show you how I do it without that. On the left side, we have 2 carbons, as you can see right here. And on the right side, there's only 1 carbon. So how do I balance that? Well, I multiply the right side by 2. So that's a balanced equation for my carbon. Next, we have hydrogens. It looks like there are 6 hydrogens on the left and only 2 on the right. So what number times 2 equals 6? That would be 3. So I'm going to multiply this by 3, and my hydrogens are balanced now. Now the oxygens, this is the hard part. Students might really need to pay close attention to this, because this is where people get stumped sometimes. Notice that we have 2 oxygens on the left. Okay? On the right side, how many oxygens do we have on the right? Can you count those up? It's not 3, it's actually 7. Do you see 7 oxygens? We have 2 times 2 there, so that's 4, plus we have 1 times 3, which is another 3. So we actually have 7 oxygen atoms on the right. 4 there plus 3 here, so it's 7. Now, what number times 2 equals 7? Well, you might remember from your algebra class that it's 3.5, right? So can I multiply this by 3.5 and say everything's balanced now? Well, I guess mathematically speaking you can, but can you really have half of a molecule? No, that's not how it works. Since in nature you don't have half of a molecule reacting. We need to have whole number coefficients, whole number ratios in this balanced equation. This is where some students get tripped up. When you have something like this that has a fractional coefficient, you're going to multiply everything by 2. You're just going to double everything to get rid of that fraction. So the understood 1 that's out here, I'm going to multiply that by 2 to make it 2. And then 3.5 becomes 7. 2 becomes, well, 2 times 2 is 4. And 3 times 2 is 6. Okay, now when you have a combustion reaction like this, those are probably the hardest type to balance. But this is balanced. If you add these up, we have 4 carbons on both sides. Looks like we have 2 times 6 is 12, so 12 hydrogens on both sides. 12 over there. And looks like we have 14 oxygens on both sides. We have 7 times 2, which is 14 on the reactant side. And then we have 8 plus 6. That's 14 on the product side too. So this is a balanced equation. Now we have one more here. Let's try this example. We have chlorines. There's one chlorine on the left, and looks like we have 3 on the right. So how can we balance the chlorines? 1 on the left, 3 on the right. Well, if we multiply this by 3, now the chlorines are balanced. what else is left? Well, it looks like the hydrogens need to be balanced. And we have, well, 3 times 1 is 3 hydrogens, and only 2 on the product side. So how do you balance 3 versus 2? Well, maybe we need to multiply the right by 3 to get 6 hydrogens over here, and multiply the left side by 2. 3 times 2 is 6, so we actually have to change that coefficient, and now we have 6 hydrogens over there. So is everything balanced? Well, not quite, because we've now messed up our chlorines. We have 6 times 1, that's 6 chlorines on the left. How many chlorines are on the right? Just 3. So we're going to have to multiply 3 times 2 to make it equal 6. Anything else? Well, now we've messed up our aluminums. We had 1 on the left, and now we have 2 times 1, 2 aluminums on the right. So how do we balance that? We put a 2 over here. So as you can see, sometimes we have to go back and forth and change these coefficients. This is almost like working a puzzle. And so sometimes you have to change your coefficients, go back and forth until everything works out. But as it turns out, this reaction, this equation, is now a balanced equation. So this is correct. Now, if you're feeling a little bit confused on these last 2 equations, it might be because you need to make a chart, a little diagram, to take inventory of atoms on both sides, kind of like we did in this last slide over here when we had these first 2 equations. And so this is a little tutorial of how to balance equations. The only way to get good at this is to practice. And so at this time, you're going to do several practice examples, and after doing several practice examples on your own, you'll probably feel a little bit more confident about how to balance equations.